So this week we're talking about soil porosity and density. So we've already talked about some of the physical properties of soil. They include color, texture, structure, and now we're going to be talking about density and porosity. So it's important to note that clay particles have much more surface area than sand or silt, thousands of times more than silt, and hundreds of thousands of times more surface area than sand particles. So here are just some lists of soil separates and what properties and behaviors they might have on soils. And of course, decomposition of organic matter is really rapid in sand. It's medium in silt. It's slow in clay. Drainage rate, of course, high in sand, slow to medium in silt, and then very slow in clay. So soil texture and water retention. So first of all, plant available water is the water that's held loosely on soil surfaces that is accessible to plants. And then there's unavailable water, which is water that's held tightly to the particle surfaces or the micropores and is never available to the plants. Field capacity is the amount of water that is held in the soil after the excessive water has drained through. Gravitational water is water that is not held in any pores and basically drains quickly because there's no tension to hold it. And then the permanent wilting point is the minimum amount of water in the soil that the plant requires not to wilt. So here's so the gravitational water would be on the left here. The soil's saturated and then it's just running through. Field capacity, the water's being held there. And then wilting point, you can kind of see the very small film of water around the soil particles. So I'm not adding the different structures on this presentation on the video, but if you look at the PDF, you'll see more details on these different types of soil structures. We touched on them last week, but there's more detail there. But it's important to note that water movement is very slow in platy, which is often the case with compacted soil, and then massive, which is basically no structure whatsoever, but very compacted. So structure can be altered by tillage or traffic, and this breaks down the natural structural units or aggregates. And if you till the soils when they're too wet, this can happen, and you can compact the soil with heavy equipment. So you can break down aggregates by tillage and rain, and the loss of organic material leads to the loss of microbiota. So basically what it's doing is it's stirring air into the soil, and it stimulates the microbes to increase the rate of organic matter decomposition. And then if you don't have organic matter, you don't have aggregates binding together, and that soil organic matter is lost to the atmosphere as carbon dioxide. So macropores are quite large. They allow ready drainage of water and air movement. These can have small roots and different organisms in them, and these are often the spaces between sand grains. Micropores are really small and usually filled with water, and the water movement is very slow, and this is where the unavailable water is held because it's held too tightly. So if you add a little clay to sand, they start filling the big pores, dividing them into smaller ones, and then water is held there. And it's really not a good idea to mix these two textures. It's much better to use organic matter if you need to deal with porosity. So porosity and permeability can range in sediments, and so sand actually has a fairly low porosity because it's got less surface area, but permeability is high. Clay has higher porosity, but permeability is low. bulk density is the mass per unit volume of dry soil. And you can see on the left here, the lower bulk density weighs less, there's more pore space. On the right, this has higher bulk density, higher weight, less pore space. And as bulk density increases, porosity decreases. So believe it or not, clay tends to have a low bulk density. It has a very high percentage of pore space, as we've already mentioned. Compacted soil, which is not the same as clay soil, sometimes clay is involved with compacted soil, is pretty high at 1.67, and you can see the pore space is 37% there. And when we do our bulk density lab, some people have very high organic matter in their soil, and believe it or not, your bulk density will actually be lower than 1.05 grams per centimeter cubed. So here's the general relationship of bulk density to root growth based on soil texture. So ideal bulk densities for clay soils would be 1.1 grams per centimeter cubed. And then it doesn't take long as the bulk density gets heavier for root growth to be restricted. And so here's just 1.0 to 1.6, that's going to be normal soils. 1.4 to 1.6, you're going to start seeing some root restriction. And then 1.7 to 2.2, that's commonly found in construction sites, and 1.4 to 2.3 is brick. So you can see construction sites do quite a number on bulk density. So basically, bulk density is the weight of dry soil over the volume of dry soil. And we'll get into this when we do this lab. So compaction and bulk density, you can see the plow layer is basically the upper layer of the soil, is usually turned under in plowing. And then just under that, you're going to see the compacted zone. Look how high those numbers are. Of course, till, that's glacial till way at the bottom there, that's pretty high, but that's super high for the compacted zone. So particle density is the mass per unit volume of soil particles. And so particle density would be measured as the weight of dry soil over the volume of water displaced. And it's relatively constant and is sometimes assumed to be 2.65 grams per centimeter cubed. So the soil porosity is the percentage of a soil that has pore space or voids. The average soil has porosity of about 50%, and those pores are filled with water or air, depending on the moisture content. Sands, of course, have larger pores but less total pore space than clay. And if both bulk density and particle density are known, then you can figure out the total porosity calculating these values. And we'll do this in lab. So causes of compaction, traffic, of course, and not just vehicular but pedestrian traffic. Social trails are quite often a problem. Tillage initially loosens the soil but lowers the organic matter, destroys the structure. And again, I mentioned that tilling when the soil is too wet is particularly harmful. And rain can actually break the surface beds and tiny bits wash into pores, forming a crust. So we've got our surface crusting going on there. That is a type of compaction. Then there's plow layer compaction, and then subsoil compaction. And here's just what the roots are going to look like under the soil there. You've got your surface crust here. You've got surface compaction, especially under wheel tracks. You can see there's no roots growing on that one side. The plow or tillage pan just below the plow depth, and then deep soil compaction. All the roots are on the one side of the plant, so that's not going to be particularly healthy for the plant, either structurally or for taking up water and nutrients.